Well, the second part, not only it's longer in terms of how many things we have to write, but it's a little bit, it requires some extra ideas. It's not just a simple plugging. I'm not going to show you the complete proof. There's no point doing this in class, but I'll show you the case, special case when m for Mary equal 2. So when we have only two solutions, so when we have only one extra solution here. When m equal 2, in this sequence of k indices, you will have only two elements, 0 and 1. For 0, the argument I have just presented. For 1, this is the argument I'm going to present right now. If you understand that argument, extrapolating that argument for any other m's, it's already routine exercise. Lengthy, not easy, but still routine exercise. Let me just, because most of the argument is a bit down, I'm going to scroll up my screen. I'll copy this polynomial down here, just move it down here because probably we will need this just to keep it in front of our eyes. But now I'm going to move the slide upwards. If you copy the statement of the lemma, keep it in front of your eyes, it will help you. The main idea, I mean, we can of course we can of course take my sequence like so, put it across this expression, but I don't think you will see the polynomial p there like as easily as we saw it here. You need something else, and this something else is here. Look at this. What I'm going to do now, I'm going to take a derivative of my polynomial, p dash of z, of this polynomial. And that's the key idea which is needed to do this case, actually. If I take this derivative, p dash, we all know how to take derivatives of functions, especially of polynomials. It's very easy, right? If I take a derivative of this polynomial, here it is. It will be r, z, r take 1. Then it will be ar coefficient from here. It should be a1, actually. It's a typo. I'll fix it in a second. Here should be a1. Let me just fix this. So here's how the derivative will be of this polynomial if I differentiate it once. If I write this in sigma notation, here it is in sigma notation. It's a sum s from 0 to r take 1. It is one less terms because you see when you differentiate polynomial, the last one will disappear. That's why we have the amount of terms is by one less. Here's my r take s, that's the one which jumped from the power here, and we reduce the power by 1. Here's my derivative. On the other hand, I can compute the same derivative from here, from this assumption. From the assumption that alpha is the root of multiplicity m. In our case, multiplicity 2. We'll just do that. The same computation, here I'm going to use the product rule, product of the first derivative of the first factor times the second factor and the other combination. So here it is. Here's a derivative of the same polynomial, but now basing on this assumption. What do I see from the second computation? I see that if I sub in alpha into my p dash polynomial, which is a different polynomial, but what I see is if I sub in alpha in this new polynomial, it will be 0 again, because here we have a bracket which vanishes, and here we have a bracket which, it's another typo by the way, it's the m is missing on the top. M is missing on the top. If I sub in alpha, it will be 0 and 0 on both accounts, and that's why we have p dash of alpha is also 0. That's an interesting observation on its own account, actually, that if you have a root of multiplicity 2, not only this root vanishes the polynomial, the same root vanishes the derivative of that polynomial. And you can actually develop this further. If you have a root of multiplicity 3, this root will vanish the polynomial, the first derivative, and the second derivative. That's a very beautiful property of roots with the higher multiplicities, something to remember. And we're going to use it now, because look what I'm going to do now. Now I'm going to scroll up my slide. Here's my left-hand side of asterisk. Asterisk was on the top of the slide. I sub in my x1 solution. Remember, I want to check that this is a solution to my difference equation. So here's my substitution. Here's a substitution. Here's the x with the index n take s. So here we went with n take s, and here we went with n take s. all of them here. Now I want to link this. I want to link this with the P of alpha and P dash of alpha, because both of them are zeros. Here's my linkage. First, I factor out as before, as in here. I factor out this much alphas. Here's the remaining bits. Now these powers, they resemble these powers a lot, but still we have this n take s, which we have to deal with. I'm going to deal with this by splitting this bracket into these two brackets, n take r and r take s. If I do the splitting, look what happens. This is the expression, this is the whole expression like so, but where this bracket is replaced with this bracket, and because this bracket is independent of the index of summation, it came out of my summation. And now the second part, where this bracket is replaced with this bracket, is it here? Yes, it is here. Here it is. And now we can see this summation, it is my polynomial, P of alpha, and this summation, it is my P dash of alpha. Look at this. There's a minor difference, there's take 1 here, but I can achieve this take 1 by factoring another alpha from this summation. So altogether we end up with the expression like this. For the left-hand side of my difference equation, I express my left-hand side of a difference equation as a combination of P of alpha and P dash of alpha, you see? And that is 0 because we have a root of multiplicity 2. And that finishes the proof of this particular case. If you spend some time with this proof, you will realize what happens when m for Mary, m equal 3. When you plug in this, third solution, there will be a way to represent the left-hand side as a combination of P of alpha, P dash of alpha, and P double dash of alpha, which will be 0 because you're looking at the root of multiplicity 2. No, 3. Sorry. I think there's another last bit on this slide, something which I already voiced when we discussed the previous slide, but now I just give you the writing of it. Now the theorem, actually it's a very deep theorem on its own. It says that any solution to a difference equation is a combination of fundamental solutions